Okay, let's see. All right, well, I don't see anybody else. Well, I guess it looks like one or two people are still joining. Okay, well, let's go ahead and get started on this practice test question then. So here's what I'd like you to do. So if you go to go to Blackboard here and the week 3 content area, then you will see a folder that has opened up called the practice test problem folder. And in that practice test problem folder, there is a document called practice test problem. Let me show you how this goes. So I'm going over here. So here we're in Blackboard. We are down in the week 3 content area folder here called practice test problem. Okay, click on that. And you should see a PDF right here, which you can then open up and download. And that is the practice test problem. Okay. If you have a printer handy, feel free to print it off. If not, just you can just work on a piece of paper, and we'll just go with that today. I did, for convenience here, put in the equation sheet. Feel free to use that as well. But otherwise, basically just we'll treat this kind of like a test to condition, so you can have something to write with, you can have a calculator, and you can have your equation sheet. If you have the paper equation sheet handy, feel free to use that as well. And then go ahead and just work the problem. And we'll take probably 15, 20 minutes for this, and then we'll come back and talk. Okay, so feel free to get started on that, and I'll check back in with you in 15, 20 minutes. So. All right, checking in here. Maybe take another 3 minutes or so. 3 minutes or so. Okay, let's see. I think we're just about on 10:40 here. So go ahead and take a pause, whatever you're doing there, and we'll go ahead and we'll briefly talk about this. I will post up the solution here. Give me a moment to do that. And let's see, where'd that window go? Okay. Okay, let's see. Okay, so I'm just going to briefly talk about the solution here. I'll post this up online. You should take whatever solution that you had, okay, and I want you should compare it against this document and make sure that you get something similar, okay? So here's the concept. Make this a little bit bigger so you can see it. So here in this problem, we were given some charges in the coordinate plane, and we needed to calculate the electric field at the location of charge Q3 and the electric force acting on that charge as well, okay? And so again, with these problems, you're going to want to start off with a good problem solving strategy: plan, sketch, calculate, check, right? That's our major steps. So, for example, in this problem, what might be your plan? Well, we've got charges, right? They're small charges, right? They're 1 millimeter in diameter. And the spacing is on the order of meters, right? So it's reasonable then to model those charges as point charges, right? So that's something you want to write down, model particles as point charges. Then you can use vector superposition, as we know, to add up the fields, okay? You could even put down the equation for the equation for the electric field of a point charge. Next up, you want to make a sketch, okay? Put in some coordinate axes. You want to put in your charges. In this case, there are the 3 charges here, Q1, Q2, Q3. And if you want, you can put in the coordinates, you can put in the charges, whatever you think is best. But at the very least, you need to put in the charges and their locations, right? And at that point, then you need to go ahead and start calculating what are the contributions to the electric field at the location Q3. That's this location right here, -1, 0. Okay. And in this case, there are 2 contributions to that. There's the contribution to Q1, and there's the contribution to Q2. Charges do not contribute to the electric field at their own location, right? Because, well, if you look at our equation here, KQ over R squared times R hat, if R is 0, you get a nonsensical result, right? So it's only really that Q2 and Q1 contribute to the electric field at that point in space, even though there's a charge there. Okay, so to do that, then we need to go down here. We're going to calculate our equations here, E1, KQ1 over R13 times R13 hat. Stick in our values here. We know K, we know Q converted to coulombs. We know the distance, that's 2 meters. And then we have to figure out our hat, right? So what's the unit vector that points from our source charge Q1 to our test location Q3, or the test charge Q3? That's going to be, we can see that in the negative x direction, that's negative I hat, okay? And if you want to, you can actually go through the calculation here as well, which I do up the top, okay? You then put that in your calculator, you get some value. Right? Likewise for Q2, sorry, I think there's a typo here. It should be Q2 right here, not Q3. And in any case, you take the K, take to multiply times the charge, divided by the distance. Now you can figure out that distance by using geometry, square root over 2 meters. You can also figure out the R hat vector, right? The vector points down and to the right, okay? There we go. And so that should be this vector right here. Again, you can work through the details here, take the difference by your test coordinates minus your source coordinates, and that should give you your value here. Should point down to the right. That's when this one does. It's a unit vector. Okay, once you have that, you multiply everything out, and you get some vector here for that vector. And again, it points down to the right as we would expect. It's a positive charge, point away from that charge. Last step, you need to sum these up, okay? And again, that's where you get the calculator out, add up the x components here, the I hats, add up the j hats as well, and we get some result. Okay, so that's the net electric field. Part B was to calculate the force at that charge, Q3, okay? And in this case then, the easiest way to do that, since we already know the field there, is to use what we know F equals QE, right? So we take that field we just calculated, we multiply that times the charge at that location, in this case the 1.7 nanocoulombs. Again, we want to write that in coulombs, that way the coulombs cancel the coulombs, we get newtons, and again, you get a result here, okay? So that's the basic concept here, how this will go. And that's the kind of thing you should be looking forward to on the exam. All right. So make sure you can do this. It's a very reasonable kind of question I could ask on the exam, and make sure you can not only work the problem but work it quickly and efficiently. Right. Okay. Again, this is now posted up in that full same folder up on Blackboard, so you can take a look at that at your convenience. Any questions here? Okay, so go through what you wrote down. Make sure go through step by step. See mark up your page. What did you do? Did you put in model assumptions? Did you make a nice diagram? Did you do the calculations and do them correctly? And again, I want to emphasize here, I do try to get partial credit where I can, and part of that partial credit usually comes from the work that you do, right? If I can see that you're on the right track, that's where you start to get partial credit. So I encourage you to write down each step, even though it does take a little bit longer. Even if you don't get quite the correct answer at the end, at least I can see what you're doing. All right, so that's an example practice problem. This you can see was quite similar to the problem we did last week. You'll remember this one, we ended up with the end of class last time. We had 3 charges, and in this case we had to calculate the electric field at the fourth point on the other corner of that rectangle. And we had just gotten almost quite to the end. We just ran out of time a little bit at the end, so I just want to give you the answer. Hopefully you were able to work it out over the weekend. We were able to calculate, of course, the contribution due to the first charge, Q1, over here, pointed off to the right. We were able to calculate the contribution E2. I pointed down along the y-axis, and then we were able to calculate the contribution due to E3 up here, down, in this case, up and to the left, because it's a negative charge. Last step is to add those up, okay? And here's the answer, okay? So just so you, if you worked it out, you can see, basically, again, you just want to write down all your I components, write down each of the vectors, okay? And then you can add up all the I components, add up all the J components, and that will give you the net electric field at this point. So in this case, it was 64,000 my I hat minus 369,000 J hat time, and that's in units of newtons per coulomb. Okay, and so you can see then you can see that seems to match up reasonably what we expect from the vector sum, right? If you look at our vector sum, we have some E1 pointing off to the right, we have some E2 pointing down. These are probably not quite to scale. I'll be honest with you. But in generally speaking, we got some vector pointing off to the right. We've got some vector pointing down. That's E2, and then we got some vector pointing up and to the left. And I think if you do some vector sum here, you'll see that yes, pointing down and then to the right is a reasonable outcome. Okay, so hopefully you got that same result when you worked it through at home. Any questions about this little example here? Okay. Again, I will, at the end of the class today, I will post up slides for all of chapter 2, so you'll have those available for later this week. All right, did want to move on today to talk about some new material, the last major topic in chapter 2, which is this idea of a motion of charged particle in an electric field. Okay, so if we have some particle of charge Q and has some mass M, and it's in an electric field, okay, and that electric field is, I want to emphasize, not due to the charge itself, it's due to other charges around it. Okay, again, electric fields do not affect an electric field from a charge does not affect the charge itself. Okay, so this is an electric field that exists at some point in space. Okay, we now put a charge at that point in space. If it's a positive charge, right, we know F equals QE, that positive charge is not going to change the direction. My force will be in the same direction as the electric field. If my charge, however, is negative, right, we know a negative value times the vector is going to change things to be the opposite direction. So in this case, E is up and to the right, but my force on the negatively charged particle is down and to the left. Okay, so now we have a charged particle, it's in an electric field, it's now feeling a force. Okay, what happens when a charge feels a force? Well, Newton's second law still applies, right? That has not gone away from physics 1. And so we know the acceleration of that charge will be the force on that charge divided by its mass, okay? And if the electric force is the only force, then what we'll get is then we can stick this result in here, QE for F, and what we get then is the expression shown here on the bottom right corner here, Q over M, the ratio of the charge to the mass of the particle times the electric field will give you the vector acceleration of the particle. Okay. So this, again, electric field is a vector, so acceleration is a vector. We know acceleration is vector already, right? So this now will tell us how the motion will go in terms of the acceleration on that particle. Okay, any questions about this slide? Right, so really just taking some things we already know. We learned F equals QE in this class. You learned F equals MA in the previous class, putting those things together. All right, well, if we know there's a force acting on a particle and it starts to accelerate, then if the acceleration of the particle is constant, right, and that is a precondition that has to be satisfied, then you can use the so-called kinematic equations. Okay? So this is something you usually cover in the first few weeks of a Newtonian mechanics course, like the one you've had. And so hopefully this is familiar to you. You can use calculus to derive these, right? So you know that if I have some initial velocity of that particle, I can take the acceleration of the particle in that component direction here. S is either x or y or z, right? It's the just a component of that. So here in this case, s equals x or y or z, right? It's just a component of that acceleration or the velocity in that direction. Then the initial velocity plus acceleration times the time interval over which that acceleration acts will give you the final velocity. Similarly, you can find the final position, right? In this case, again, x, y, or z is the initial position plus the initial velocity times this time interval plus 1/2 times the acceleration component times delta t squared. And sometimes if you can actually, if you combine these first two equations together, eliminate the time, you get the third equation, which is sometimes convenient if you don't know the time interval. Then you can calculate the final velocity squared is going to be the initial velocity squared plus 2 times the acceleration times the displacement of the particle, the change in position in that position coordinate. Okay, so hopefully these look familiar to you at the very least. If you don't remember them too well, go back and look at your notes from a previous course. But we do expect that you know these and can use them. Any questions or comments about the kinematic equations? Okay, again, key assumption here is the acceleration must be constant. If the acceleration is not constant, you cannot use the kinematic equations, or you can, but you'll get the wrong answer, right? So don't do that. Okay, so let's take an example problem here. So I want to talk a little bit about the so-called ionospheric electric field. So this is an interesting phenomenon. So on our planet, we have what's called, there's an atmosphere that surrounds the planet, which is it's basically gas, which is attracted to the planet by gravity. And that gas is composed of atoms. Those atoms, though, when they are hit by particles and radiation coming in from the sun, can become ionized in the upper part of the atmosphere. There are several actual layers of ionization that occur at various levels throughout the ionosphere. And these layers are called the ionosphere. So it's basically layers of ionized gases. Now, so what happens is, again, the atoms are in this space. Some, say, a charged particle comes in, boots them out, the electrons out of the atoms, and they would otherwise escape into space, but they're negatively charged. These ions are now positively charged, and so they're attracted to the ions, okay? And this, they're separate, but they're attracted. So we now have a separation of charge, okay? And that separation of charge creates a polarization electric field, right? We know that whenever we have separation of charge, we get an electric field. Okay, so basic bottom line is in the ionosphere of charged particles in the atmosphere above us, we get an electric field. Okay, so with that as a preface, then we can now start to try to do some calculation. Okay, so it turns out that you can measure this electric field, and at least some part of the ionosphere, it was measured to be around 1.09 times 10 to the negative 6th newtons per coulomb in the upward direction. Okay, so that's experimental data. Basically, they sent up a rocket, and the rocket has a little meter which can measure electric field, and you can measure the electric field that way. All right, so here's some calculations I'd like to see if you can try to do. So part A here is, what is the electric force on a hydrogen ion okay? Uh, if we have some, we know that at least part of the atmosphere contains some hydrogen. Not most of it, but there could be some up there. We'll try to keep things simple to start with. What would be the electric force on that hydrogen ion? And first of all, you want to think, what is actually a hydrogen ion, right? Think about that for a moment. If I take a hydrogen atom, I boot out an electron, what do I have left? Second of all, what then is the gravitational force on that same hydrogen ion? Again, and you can go ahead and assume that the acceleration of gravity is 9.8 meters per second squared. It's probably not exactly true. As you get a little further away from the Earth, it does start to change a little bit. Again, let's try to keep things simple here. And then finally, the real question I want to know is, will the hydrogen ion go up or down? Right. So I'll give you a minute here to see if you can figure this out. Again, what's the electric force on the ion? What's the electric gravitational force on the ion? And will the ion go up or down? If you do get an answer for any of these, feel free to put it in the chat. Checking in here, how are we doing? Questions here. Again, if you have questions, put those in the chat as well. Does anybody have an answer for either A or B, at least? A or B? Okay, well, let's at least try this out. Maybe I'll get you going here, and you can, if you haven't finished, we can at least compare going results here. So in this case, we want to figure out the force on a hydrogen ion, right? So gave you a hint here. This is the mass of a hydrogen ion. What is a hydrogen ion really, though? If you wanted to give me, it's what is hydrogen made out of? I remember from chemistry class. What's the atomic number of hydrogen? Yeah, exactly. It's one, right? One proton, one electron, right? So if I take off the electron, what do I have left? Well, just the proton, right? And so that's where this number comes from. This is an equation. It's on the equation sheet. If you look on the mass of proton, that's the number you'll get. Okay. So indeed, I can then calculate the force on that hydrogen ion because I know it's a proton, and proton has a charge of what? Well, just the fundamental unit of charge. That's the charge of proton. Okay, so here, if I just look at the magnitude of the force, F sub E here, that's going to be equal to the charge of the proton, which will be our fundamental unit of charge, times the magnitude of the electric field here, which is the value given up here. So that's going to be equal to, in this case, we'll take the value here, 1.6 times 10 to the negative 19 coulombs. That's our fundamental unit of charge. Again, that's on the equation sheet as well. And multiply that times our value here, 1.09 times 10 to the negative 6th newtons per coulomb, right? And you can plug that in a calculator. I got 1.74 times 10 to the negative 25 newtons, okay? Super, yeah, okay. Looks like we got at least one other person who got the same result. That's great. Super, okay. Hopefully anybody else get that same result? Okay, well, at least one person did. All right, let's move on here then. Okay, let's look at the gravitational force. That's probably a little bit easier problem. So in this case then, gravitational force, that's going to be equal to the magnitude of that gravitational force will be equal to, well, mg, right? Again, to our first approximation here. And so in this case then, the mass is the 1.67 times 10 to the negative 27 kilograms. It's pretty small, it's just a proton. And g is 9.8 meters per second squared. And so again, if you multiply those out, okay, I ended up getting 1.64 times 10 to the negative 26th newtons. Right. Did anybody get that? Okay, super. All right, at least a few people got that. Great. Okay, so question is, does the hydrogen ion go up or does it go down? I'll put the answer in the chat here. We got one vote for up. Up. Okay, yeah, looks like we got ups coming in. Yeah. Oh yeah, I agree. Up. Yeah, definitely up. Here we see that this is the force is going to be the upward force, right? Because it's an upward directed field, right? And we know gravitation acts down, right? But in this case, this one's bigger, right? So it's quite a bit, almost order of magnitude bigger. And so it will go up, right? So here we go. The magnitude of F sub E is bigger than the magnitude of F sub. Okay, so that's interesting. Okay, so that means the electric field that's in this area will actually push the ions upwards away from the Earth. All right, any questions about this result? It's part two of the problem in the next slide here. Okay. All right. So before we do that, though, I want to play a little video for you. Hopefully this will play. I may need to, hold on, I may need to reshare out. Give me a moment. I may not have hit the right button when I set this up. Give me a second. Let's see. Yes, okay. Let's share that out. Okay, there we go. All right, there we go. All right, I'm going to play a little video here. Hopefully the audio will play. Just to play. Let's see. Let's see, maybe not. Where's my arrow? Here we go. Here we go. There we go.
It's called the ambipolar field, and it's an agent of chaos. It's an electrical field. It begins at about 250 kilometers above your head, and it keeps going. The atmosphere up there is different than the atmosphere down here. Thinner, right? There's less of it. So think about just one atom. Here it is. The sun shines on it, it breaks off this electron. So now we have this negatively charged electron and this positively charged ion, and the two are attracted towards each other. The electron would happily escape all by itself, but the ion still feels the big tug of gravity. So as the electron tries to pull away, the electric force forms between the two to restrain it, to keep it from escaping. And it also helps pull the ion upwards. The field works in both directions. It is ambipolar. Imagine you're walking a dog, and you've got a tiny, tiny little dog, and it's pulling on a leash. That dog's going nowhere. This ion and electron pair that you've been thinking about, they're only one in an enormous sea of the ionosphere. But overall, because gravity's pulling down on the ions, it adds up. And over a large distance, you get this field forming. It's like this conveyor belt that's countering gravity and lifting the ions up so they can escape to space, which is why it may have had an impact on the evolution of the atmosphere.
Okay, so hopefully you were able to hear the audio there. And I know there's a little bit of a disconnect between the audio and the video there, but the basic bottom line here is that we get the separation of the electron and the ions, but there's this upward force pushing on the ions. Okay, so can we figure out then what the acceleration would be? If there's a force on the ion, there must be some acceleration as well, right? So I'll give you a moment here. Can you now calculate, based on what we've just done here, what will be the net acceleration? Because we've got two things acting on the particle now, but what will be the net acceleration of the ion? And then beyond that, then how long will it actually take to, once you get that acceleration, it's going for that speed of that particle to be greater than the speed of sound in air, which is around 340 meters per second, assuming constant acceleration. So I'll give you a moment here, figure that out. If you do get an answer, feel free to put in the chat here for either of these problems. Yeah, so it's the same parts. This continuation, the same problem here. We are talking still about the hydrogen ion, right? So this is part D of assuming that you've done A, B, and C. Okay, that's some answers coming in here. See if anyone else has the same or different answers. Any other answers coming in here? All right, seem to have some disagreement coming in. Let's see. All right, well, let's take a look at this one then. So in this case, then here, so back here and put my pen back. And okay, so what we have here then is we want to calculate the net acceleration, which means we need to know the net force, right? And so in this case, then we're going to have the force of the gravity, sorry, the force of the electric field, which is acting upwards. So that'll be sort of, if we sort of a little positive set of coordinate system, sort of with y positive being up, then we'll have, in this case, the force of the electric field plus the force of the gravitational field. That will be the 1.74 times 10 to the negative 25 newtons times, say, j hat, and then add to that the negative 1.64 times 10 to the negative 26 newtons times j hat. It's in the opposite direction, so it's negative. And so in that case, then you end up with about 1.58 times 10 to the negative 25 newtons, and that's in the plus j hat direction, right? So it's upwards, as we said before. So okay, so that's my net force. Acceleration, right? Is going to be the ratio then of the force on that force on the our particle here divided by its mass, and the mass we said was the 1.67 times the 10 to the negative 27. So, but then here we get 1.58 times 10 to the negative 25 newtons divided by the 1.67 times 10 to the negative 27 kilograms. Okay. And let's see, I ended up getting about 94.6 or so meters per second squared. Okay. Now, is that a high acceleration or a low acceleration? How would you consider that? If you were in a car going at 94.6 meters per second squared, how would you feel? Yeah, someone putting a comment. Yeah, that's fast. So yeah, I mean, if you think about it, if you think about how many times, it's certainly greater than the acceleration of gravity, right? So how many times greater is the greater acceleration of gravity? So you divide this by 9.8, I got about 10.6 g. Okay, so it's 10.6 g. it's a good sized acceleration, right? You're going to feel that. You're going to feel pressed up against the back of your seat if it's a positive acceleration, quite a bit. All right, so yeah, we're accelerating upwards at a pretty good rate. All right, so last part of this then, how long will it then take to break the speed of sound in air? Again, assuming this acceleration is constant. Anybody get an answer for that? Okay, got some answers coming in. Let me know if anybody else gets the same or different answer here. Okay, looks like we're getting some agreement. Okay, yeah. All right, well, let's take a look. So in this case here, we know the acceleration. Again, if we assume constant acceleration, that means we can use kinematics, okay? And in that case, we know that the final velocity is going to be the initial velocity plus the acceleration in a given direction. In this case, let's take this to be the y direction, times the time of interval, right? And if we assume that it starts from rest, then we'll have, then we can solve for delta t. Delta t becomes equal to the final velocity in the y direction divided by the acceleration in the y direction. And so in this case, we want to know how long will it take to get to 103, 140. We can divide that by the acceleration we got up here, 94.6 meters per second squared. And indeed, I got about 3.6 or so seconds. Okay. So pretty quickly, that ion is going to accelerate up to sort of sonic or supersonic speeds, okay, which is interesting. So, and in fact, these have been absorbed in the atmosphere as sort of supersonic jets going away from the atmosphere, especially near the poles, where this is probably the predominant effect. That's where the ionization tends to be a little bit more intense. Okay, so indeed, if you go back to the original paper that this was published, they come up with a value which is reasonably close to this value here in the paper. They do a little more sophisticated analysis, but that's the basic idea here. Anyway, nice example of using kinematics to solve a simple problem here, or at least a problem with some simple simplifying assumptions, right? Any questions on this problem? Okay, let's see. We've been at this about an hour. Let's take a 5-minute break. We'll come back at 11:25, and we'll continue onwards. I want to do another more sophisticated problem, looking at motion of charged particle. So we'll be back at 11:25. Oh, sorry, my bad. Yep, I got turned off here. All right, let me start again. So my apologies. Go back to the previous slide. So again, the problem we have here is a water droplet, okay? And the water droplet is it's an ionized water droplet, so there's missing some electrons, and it's in between these two plates. Two plates have a uniform field, okay? And the question we want to know is where does the droplet hit the table? Okay, so let's hopefully, sorry about that. Always hard to know what everyone's hearing or not hearing when I'm doing this online. Okay, so yes, so two assumptions I want to make here. First of all, the model assumption that the field is uniform inside between the plates. Okay, and so I just sort of drew that in here. So we're just going to assume that even near the edge of that plate, that field's going to be uniform. And second of all, we're going to model the droplet here as a point charge and as a point mass. Okay, so we don't want to deal with the spatial extent of that charge or mass. Okay, so that'll be a good starting point, and then we'll go from there. Obviously, the visualization step is already started here. Well, let's call it sketching instead. I think that's probably better. Better way to keep it consistent here. Let's call it sketch. Okay. All right, so we're going to sketch this anyway. Obviously, the field, that's one good thing we'll do. The other thing we're going to do is we're going to put in a coordinate system, right? So you can pick wherever you want. I'm going to pick mine to be 0 at the bottom right below here, right below that water droplet. So I'll have so that's not good. Let me make sure if I can erase that. I want to go off to the side like that. Let's go, let's see. Oops, where's my eraser? Printer, eraser, there we go. Let's get rid of that. I want to go try to draw a straight line here. Okay, straight line, straight down, more or less straight down. Okay, it's going back and forth, but hard to draw freehand. That's what it's supposed to be. My coordinate axis Y, coordinate axis X. Okay, and so that's going to be our starting point. We want to have this coordinate system. All right, so another thing we might want to do here is we want to look in our sketching step is we want to look at the forces acting on the particle. So for that, we might want to draw a little free body diagram, okay? So in a free body diagram, what you have is, of course, just a sketch of the forces acting on the particle. So if I do a little sketch like this, here's X and Y direction. So what are the forces acting on this particle? Well, we're going to have gravity, okay? Which way does gravity act? Well, it acts down, right? So if you draw that in, maybe I'll do that with I'll do that with red. How about that? So force of gravity is going to be acting down like this, okay? And then we'll have also acting to the right, we'll have the electric field, which will be off this way. Okay. So how do I know it's off to the right? Well, we said it was a particle and it's lacking electrons, right? So some of the electrons were taken away, which means that the net charge on the particle should be positive, right? So it's a positively charged particle. We know F equals QE, right? And so if Q is positive, the force should be in the same direction as the electric field. That should be off to the right. Okay, so I may not have drawn these to scale, right? I don't know what the values are yet, but at least the directions we know should be down as gravity, right for the electric field. Okay, so that's a good starting point. We can always go back to the sketching later on. Let's go in and do take a look at the calculating step now. Okay. All right. So a few things we can write down. So first of all, we can calculate the electric force, right? Electric force should be QE, right? And we can figure out the charge, right? And we know the electric field, so we should be able to calculate the electric force. What else? Well, we can also calculate the gravitational force, right? From our free body diagram, and that's going to be mg. Okay. In this case, we need to make it a vector, so in our coordinate system, up is positive, so down is going to be negative j hat. Right. All right, so those are our forces. Those are all the forces acting on the system. And so we can now go ahead and calculate the net force, right? And set that equal to mass times acceleration. That's Newton's second law, right? So Newton's second law says the sum of the forces acting on the particle has to equal the mass times acceleration, right? Now, in this case, it's a little more complicated than our previous problem because we have multiple directions of motion, right? We've got some potentially X motion and some potentially Y motion, right? So we can, again, break this up into sort of two parts, right? We've got sort of some of the forces in the X direction, and then hopefully this will be coming back a little bit from this same kind of problems you solved back in Newtonian mechanics, the mass times acceleration in the X direction, and then the sum of the forces in the Y direction equal the mass times acceleration in the Y direction, right? Okay, so this is kind of our basic setup. We get essentially two equations we have to solve. I'm going to go back. I'm going to go up here now. Continue the calculate step up in this corner. All right, so we essentially have two directions to worry about. We've got X direction equations and we have Y direction equations. So let's consider these sort of separately. All right, well, what is the force acting in the X direction? Well, it's just the electric force, okay? So in that case, the electric force here, if you like, we can write it this way, Q, the magnitude of E times I hat, right? That's another way to look at this. So essentially we're going to get QE, that's going to be the force in the X direction, and that's going to be equal to the mass times the acceleration in the X direction. That's the only force acting in the X direction. So that's the only one we have to worry about. And so you can see immediately we can solve for the X component here. E sub X is going to be Q over M times E. Okay. Here I'm using E. E is going to be just for shorthand. E without a, it just means the magnitude of the electric field. Okay, so that gives me acceleration in the X direction. What about in the Y direction? Well, in the Y direction, what are the forces acting in the Y direction? It's just gravity, right? And so here, if we look at the magnitude of the force, it's going to be minus G, right? Why minus? Because we have a minus J hat right here, right? Force acting down in our coordinate system. And that's going to be equal to mass times acceleration in the Y direction. Can we solve for the acceleration? Yes, we can. You can see immediately the masses actually cancel out. And what we find is that the acceleration in the Y direction is just, well, downward acceleration of gravity. All right, so now that we have our accelerations, we want to take a look at this. I'll ask you the question, is the acceleration constant? Feel free to put an answer in the chat here. Is the acceleration constant? Yeah, some answers coming in here. Yep. Yes. Yeah, I agree with that. Yep. Yeah, definitely constant here. We see, of course, gravity is constant. Electric field here is constant. Q is constant. M is constant. Everything's constant. So in this case, then we see that the acceleration is constant. And the reason we want to determine that is because, of course, that means we can use kinematics to solve the problem then, if that's the case. Okay. Okay. So, and that's a tool in our toolbox we already know how to use. Okay, so maybe call this step 4. Step 5 then is going ahead and using kinematics. Okay. Again, so again, here you're going to have to kind of draw upon some of your previous work. Usually when I solve kinematics problems, I like to make a table, kind of write on all the equations, sorry, all the variables that that I have in my problem, some of which I know, some of which I don't know, I need to find, and then we can kind of work it out from there. So let's think, we can make 2 columns, one for X information, one for Y components, X components, Y components, and then on the final values, the initial values, and position, final velocities, initial velocities, the acceleration components, and there'll be somewhere on the bottom here, delta t for time. Okay, so maybe we can make a table that kind of looks like this. I have a hard time drawing straight lines here freehand, but you get the idea. Actually, I'm gonna, in this case, the time, there's only one time, so I'm gonna erase that here. Okay. And so we'll make it like this. Otherwise, this will be good. Okay, so basically, we're gonna have a little table like this, and we can try to fill in the table. Okay. All right, so we can go through and try to figure out what do we know, what do we don't know. So let's take a look. For the final, we don't know the final x coordinate. That's actually what we're trying to find, right? We want to know where does it hit the table. In this coordinate system, we do know that the when it hits the table, that's what we mean. Y equals 0 means it hits the table. So, but here's what we want to find. That's actually what we're looking for, the final x component. Initial values here. Well, we know that we start here, the way we define our coordinate system, we started at x equals 0, and we started up here, and I think in the problem statement, it was 2 centimeters, if I remember correctly. These are 2 centimeter tall plates. So in that case, that'll be 0.02 meters. All right, okay, we don't know the final velocities. We may or may not need those, but we don't know them. We do know the initial velocity, which is, the particle starts at rest, so there's no component in the x or y direction, just starts at rest. And we do know the accelerations. We already calculated these out, so in this case, in the x direction, it's going to be q over m times e, or we can find them. And here in minus g. And then lastly, we don't know the time of the fall. Okay. All right, so this kind of just helps me organize all the things that I know or don't know about my problem. So the goal now is to try to figure out, okay, well, what can I do about that? How can I take the things that I know and try to figure out something I don't know or that I want to get to? Again, what I want to get to eventually is the final position, x sub f. Right? Any thoughts here about how we should proceed forward? What might be your next step here? What could I possibly compute given what I know, either in the x or y direction? Okay, we know we can solve for the acceleration. I'm gonna put that numbers in at the end. So, but yeah, that's a good thing. We will get the accelerations. What else? I'm looking to get some of these other quantities here. Maybe what will help me eventually. I want to get to this x position. Well, what would I need to know to calculate the final position in the x direction? Yeah, q we can also calculate. We'll do that in a moment. Okay, we can also get the mass and charge of the droplet. We can do that. Yep. But I want to focus here on these other quantities here in this table, right? So I want to solve for some of the quantities in the table. Okay. What would I need to know to calculate the final position in the x direction of the particle? Do we have an equation for that? Let's go back and take a look at our equations up here. Let's see. Here we go. All right, so if I take a look here, I want to know, in this case, x sub f, okay? So to get x sub f, I need the initial position, initial velocity, and the time and acceleration, okay? So here's the thing, though, we don't know the time. We don't know the time of fall. Okay. So, but if we did, right, if we did know the time of fall, right, we know the x component of the acceleration, we know that there's no initial velocity, we know initial position, so we would be good to go. So how could I then, is there a way I can solve for the initial time of flight, or sorry, the time of flight, the time of fall, the delta t here, given what I know? Let's go back and look at our equations here. Let's see. So I need to get delta t. If I get delta t, I'm good. What if we look in the y direction? Okay. Can we get delta t from looking at the equation in the y direction? Well, let's take a look. So let's write down at least write down the equation. Y sub f is equal to y sub I plus v yi times delta t plus 1/2 a sub y delta t squared. Okay. All right, let's see what we know. So we know y sub I is 0.02 meters. Okay. I'm just going to leave it in equation form for now. We know what that is. We know that there's no initial velocity. Let's see right here. Okay. So that goes away. And we have 1/2 a sub y, which we know. It's just g. And in fact, I'll just put that in there. I should put that in there. Let me go like this. Pointer options. Okay, so put a minus g here, and delta t is here. Okay, sorry, can you hear me now? Sorry, something happened with the network there. Just dropped out for a moment. Okay, we're back. All right, so basically then I can go ahead, I can take this equation, I can solve for delta t. Okay, so let's go ahead and do that. I'm going to move this to the other side. I'm going to get 1/2 g delta t squared. And I'm going to divide both sides by 1/2 g, and then take a square root. And if I do that, I'll get, let's see, I'm going to 2 y sub I over g, square root of that. Okay, so that's going to be the time of fall, how long it's going to take for it to accelerate downward due to gravity, because that's the only force acting on it to make it go in that direction. All right, so once I have, though, delta t, we can see right away that I can calculate the displacement in the x direction. So that's going to be x final is equals x initial plus vx initial times delta t, 1/2. In this case, the q e m over m times e times the delta t squared. So delta t squared. Okay. So if we stick the values in here, what will we get? So x final, that's what we're looking for. X initial, we said was 0. Okay. Starts over here. And then there's no initial velocity, 0. So we can put some things in here. 1/2, we already have the Q over M E. T squared is actually equal to T squared is equal to 2yi over G. So we can stick that in here, 2yi over G. Okay, so we're going to multiply this all out. You can see the 2's cancel, and we end up with just Q over M E y sub I all over G, like that. Okay, that's going to be our final position. Okay, and I'm just leaving everything in simples here because it gets really messy pretty quick if you put in all the numbers. So I'm just going to try to leave it in simples as long as possible. But we basically solved the problem now, so let's go ahead and plug in some numbers and we'll see what we get. Okay. Any questions here though so far? Okay, I'm going to go to the next slide here. I'm going to rewrite what we had up in the previous slide. So x of f was equal to q over m e y sub I and g. That's what we had. So let's calculate then. Number one here, q, we need to calculate that out. We need that here. We said that's going to be 5 times 10 to the 5th electrons. And that's going to be times the charge on each electron. So that's 1.6 times 10 to the negative 19 coulombs per electron, right? And you can see right away that multiply these together, I'm going to get coulombs. And I got, and you can check this at home, 5 times 1.6 is 8. And then from this, if you times 10 to the negative 14 coulombs, should be a 14. Okay, so that's our charge. What else? We need to get the mass. What's the mass of that? Well, if I know the density of the particle times its volume, right? We're told it's a 0.1 millimeter diameter water droplet, or radius. I think it's a radius. Then we can calculate the mass, right? So let's do that. You can look up the density of water. It turns out to be it's 1 gram per cubic centimeter, which is basically 1,000 kilograms per cubic meter. And when we multiply it, let's assume it's a spherical water droplet, and the volume would be 4/3 pi r cubed. In that case, that's 1 times 10 to the negative 4 meters. That'd be 0.1 millimeter. Okay, and that's cubed here. And let's see, again, you can check this at home. I got 4.18 times 10 to the negative 9th kilograms. So pretty small, but measurable. All right, let's see. So what else do we need in this equation? We got Q, we've got M. We need to get, we should write down, so we know E, we're given E was equal to 4240 newtons per coulomb. And we were given Y sub I, that was 0.02 meters. That's the height of the plate. And then 5, of course, G, we know 9.8 meters per second squared. Okay. And so, yeah, we should be able to put all these things together. And again, you can check me here, but I got, let's see, 3.3 times 10 to the negative 4th meters, which is about 0.33 millimeters. Okay, so just by sticking all these values up in the equation up here. So yeah, I mean, it's not a lot of distance, right? 0.3 millimeters, pretty small, but it's also a pretty small water droplet, not very highly charged. So particle moves slightly in the x direction, as we might expect. I think here it's not unreasonable. Okay, so a little more sophisticated problem here, a little more sophisticated in the sense that it more parameters, motion in both the x and the y direction. Okay, but these are the kinds of problems you have solved previously. That the kinematics part of it hopefully is familiar to you. The only real change now is that we have the ability to have not just one force like gravity, but we can have multiple forces, including say electric force in this problem. Here, gravity really dominates over the electric field, so it falls much quicker downward than it does to the right, but there is some displacement. Okay, any questions here? Okay. Well, hopefully give you some examples of the kinds of things. We'll have some homework coming up too about this as well. There are applications of this kind of these kinds of forces on charged particles. Here's just one example. There's many, but one of them is electrostatic precipitators. So, for example, if you have a coal-fired power plant and you are burning coal, you get a lot of ash that comes out of that effluent stream. You typically don't want to pump that straight out into the environment. That's not healthy to breathe. So, one of the ways that you can use physical filtering. But when you get down to pretty small particles, sometimes the physical filters don't work as well. And so one of the things they will do is they'll have a charged filters, which help to attract the particles, the ash particles. And then in this case here, you see you have an initial filter, you have a charging grid, which charges up the ash to be positively charged, and then use a negatively charged grid to track those ash particles to the filter, thereby leaving you cleaner air on the output. So the idea is that you're precipitating out the particles using electricity, hence the name electrostatic precipitator. Okay, so that's one example about how you might use this technology to do something practical. Okay, let's see. At this point, I think I'm going to go ahead and we'll take a pause here. Do you want to do a little bit of review for the exam? That pretty much brings us to the end of content for the chapter. I mean, do you want to do a review exam? Yeah, review. Okay, great. Okay, because I can do some other things too. All right, let's hit some of the highlights here. Again, I'll post these slides up. In fact, they're already posted up. So the exam, again, covers chapters 1 and 2. Okay, so we haven't really got to chapter 3 yet, so we're going to put that off to the next exam. So just some reminders about some things that we've covered. Okay, so first of all, chapter 1, preliminary materials, but we did cover a few things in there. So for example, metric prefixes, you should know the metric prefixes, starting down with pico, nano, micro, milli, and then of course higher ones as well, kilo, mega, giga, that kind of thing. You should know sort of discussion of frequency in particular, and a little bit about the radio spectrum. And also we talked about how to calculate the relationship between wavelength and frequency for an electromagnetic wave. In particular, basically you take the speed, okay, in this case the speed of light. If you don't have the frequency, that gives you the wavelength. So here, if we approximate the speed of light is about 300 million meters per second. If you take that divided by the frequency in megahertz. That will give you the wavelength in meters, for example. Okay, so just go back over slides for that. Not too much in chapter 1. Chapter 2 has really started to get a little more content. So things you should know, of course, charge model, right? So some basic things about how charge operates, that there's two kinds of charge. We now identify them as positive and negative. We know that like charges have repulsive forces, unlike charges have attractive forces. You should know it's a long range force. We now know that's governed by Coulomb's law, right? We didn't when we first talked about this, but we do now. You should know what neutral objects are, that they have equal amounts of kinds of charge. And you should know what conductors and insulators are, right? That conductors conduct charge easily through them, whereas insulators do not. Okay. You should know about basic charging and discharging mechanisms. So you should know that if you rub two things together, you can charge them up. You should know that you can do charging by induction, right? That was our method where we basically polarized an object and then grounded it. And in that case, you pulled the charge off of the object without actually touching it with a charged object, right? That was charging by induction. And of course, this term grounding, which basically means touching either with your finger or actually connecting it to ground, which acts like sort of a reservoir for charge to pull charge away from an object. And all this we discussed sort of in the context of this visualization technique, storyboarding. So I would expect you to be able to do some simple storyboards. If I give you a scenario, make some drawings about what's going on in that system based on our charge model, based on some in the charge in the systems. Okay. Let's see, we talked about conductors and insulators already, but we also talked about how charged objects are attracted to neutral objects. Okay, so you should know that it's a polarization force which actually caused that. The charges polarize the atoms. If it's an insulator, if it's a conductor, it actually will move the charge from one side to that of that object to the other. And because one charge is a little bit closer than the other charge, that gives you this net force. Of course, we know by Coulomb's law, the attractive force here will be greater than the repulsive force, thereby attracting these objects, the neutral objects, to the charged objects. Okay, we saw that again, paper bits with the and the foil bits with the styrofoam cup. That was our example. Again, if you have questions about any of these things, feel free to stop me. Field model, yes, of course, you should know what an electric field is. We talked about that a lot in this chapter. And you should know that the electric field can be defined as the charge on electric force on an object divided by the charge of that object. Or you can turn that around. So that's the equation at the bottom here. Or you can turn that around. You can also know, if you know the electric field, we can calculate the force. We did that in the example today, right? So definitely something you should know. You should know how to do some basic field line diagrams and field vector diagrams. These are field vector diagrams, right? You should be able to sketch these out. We did an example of that with the dipole in class. And of course, you should know the electric field of a point charge, right? In this case, 1 over 4 pi epsilon naught q over r squared times r hat. Definitely need to be able to calculate that. Here, then we also talked about what to do with multiple charges as well, right? So we're going to take, if we have this idea, or this concept here for the field of a point charge, we can combine that with the principle of superposition. And by doing a vector sum of all the contributions, that will allow you to calculate the electric field at a point in space, right? Obviously, we've done an example of that in class. We did the example today, something you should be able to do. Just a reminder about r hat, right? So definitely you need to be able to calculate radial unit vectors to solve some of these problems. And again, the key points here, you need to know the source coordinate, the test coordinates. Source charge is the charge that's creating the field. The test location or test charge is where the charge is located at, where you're trying to calculate the force on, or where the electric field is. And once you have those coordinates, you take the difference here. It's always test minus source, right? And you can plug into the formula here, okay? Again, always try to make sure that your calculated values match up with what you see in your picture. Right? That's why the pictures are so important. R hat always points from the source charge to the test location, regardless of the signs of the charges, right? Really only as a function of geometry here. No units to R hat, right? No units to R hat. All the units come from the other parts of the equation. And then, of course, here's our problem-solving strategy for multiple point charges. So again, we typically are going to be modeling our objects as point charges. In most of these cases, you want to draw a nice picture, as we've seen today. Coordinate system, identify the point where you want to calculate the field, draw the electric field components. I highly recommend that if you can. Try to really help yourself out with the diagram. Then you want to do the calculation. You want to calculate the vector components, or the vectors or the vector components, and then add them up so you get the net field at a given point in space. At the end, of course, check yourself, right? Make sure you have units, right? You should know the units of net of electric field is Newton per coulombs, units of force, newtons, units of acceleration, meters per second squared, right? You lose points if you don't have units for things that need units. Coulomb's law, yeah, we talked about Coulomb's law as well, right? So sometimes you can directly calculate force between two charges if you just use Coulomb's law. And so in some cases that'll be quicker if you don't know the electric field already. If you do, maybe quicker just to use this approach up here. So you should know Coulomb's law. Key point here is it falls off as r squared. So as particles get further apart, forces decrease. Yeah, and we mentioned about field vector diagrams. You should also know about field line diagrams, right? So this idea that these field lines are everywhere tangent to the field vectors. They are denser where the field is stronger, and they never cross, right? But they can originate on positive charges and end on negative charges. Again, I could certainly ask you to say sketch out a field vector diagram or sketch out a field line diagram. That would be a reasonable question to ask. And then it brings us to, of course, the material we covered today. This idea that we can, in fact, if we know the force acting on a charged particle, we can calculate acceleration. And if that acceleration is constant, we can use kinematics to try to do some solving for the motion of that particle. Okay, I think that's the last slide I had. Yep. Any questions about any of the content here? In terms of general format, usually have a mix of questions, usually some multiple choice questions, perhaps like the ones you've seen on quizzes or in class. Usually could be some, sometimes I'll have some multiple choice questions where you have to explain your answer. So you have to kind of use physical principles or diagrams to explain an answer. I've had visualization questions before, like the ones I mentioned already. And then, of course, calculation problems like the one we had today in class as well. That would be also reasonable to expect. Yeah, exam review. Yeah, thanks. Yeah, so the exam review is posted. Let me see. I thought it was posted. Let me check that one more time here. In the should be in the week 3 folder. Let me see. Where is that? Is that here? Let's see. Yep, I'll post it up right now. Okay. Let's see. Exam review. Hold on. It should be available. So hold on. Yep. Nope. I got it. I'll make it available right now. Hang on. I didn't make it available. How about that? Let's see. Okay, yeah. So if you look now in the week 3 folder, there is a an item there called Exam 1 Review. It's got these review slides. It's also got a study guide in there, which is a little more detailed. And there's actually a list of practice problems if you want to do some more practice problems in there, preparation type problems from the textbook. And at the end of the textbook chapter, there is a the odd number problems have solutions at the end of the. Yeah, and I will be also posting the slides from chapter 2 as well. As soon as I finish chapter, I'll post those up. So I'll post those up those will be in the week 2 folder, which will be sorry, the chapter 2 folder, which is in the week 1 content area. Let's see. Other questions here. Are the formulas for charge segments and charge shapes of fields covered in chapter on the exam? Yeah, if we haven't talked about a particular geometry, it will not be on the exam. So other than the plate, we talked about a plate of such a uniform field. That's obviously you don't do any calculation for that. But yeah, the other kinds of things, more complicated things, those are not going to be on the exam. Let's see. Will we have again, no, we will not, but we will have class. I don't anticipate we'll have it virtual again on Thursday, but if we do, then yeah, we'll push off the exam for till the next time we are in class in person. Other questions here? Okay. Yeah. So yeah, when I post up the slides up from, it'll have everything I've written on the slides during class time. That'll all be on there. Yeah. I do that usually at the end of each chapter. Try to get that up for y'all. Okay. Let's see. I'm going to go over here to the next set of slides. I think is what I wanted to talk about. Okay, well, we have a little bit of time left today, so wanted to at least get started a little bit on electric potential, so we can set up to continue this on Thursday. So let's see, sorry, is there a comment or question here? No, okay. All right, so yeah, so we've so far been talking mainly about electric fields, right? Electric fields and electric forces, right? So it's kind of what would be called sometimes from the dynamics perspective. So we're looking at forces acting on particles and trying to be able to calculate that out. We've made good progress in that regard. But as you know from previous studies in physics, that's not the only way to solve physics problems. And in fact, the other major perspective is to look at it from an energy perspective. And so it turns out you can do the same kind of thing with electric phenomena. And that's what we're going to talk about then, start to talk about in this chapter. So the goal of this chapter then is to calculate and use the electric potential energy and a new term which we're going to call electric potential. Okay, so that's where we're going here. All right. But before we get into that, I wanted to do a little bit of review here because I know it's probably been a little while since you thought about energy in terms of a physics perspective. Okay, so let's do a little bit of a review of some of these key terms here. So first of all, I want to talk a little bit about work. Okay, so work in physics has a very specific meaning. Does anybody remember how do you calculate work? Feel free to answer in the chat. Put up your mic. All right, so yeah, some of you are putting in force times distance, and that can be the definition of work, but we want to go over a little bit more general than that. So let's think about it this way. So I've got some kind of particle, okay, and I'm exerting a force on that particle like this, and that particle is going along in a particular direction, maybe along a path, okay, and at every point along that path, it might have a different force and a different displacement, okay? So something like this, okay? And we want to know how much work does it take to move the particle from some initial position to some final position along that path, okay? So in general, the work done is going to be equal to the integration of from some initial position, here we're calling point I, to some final position, point F, sorry, here, and it's going to be the force dotted into the displacement. That's really our most general definition, okay? Now, in the special case where the force is constant, right, then with constant force, we can then pull the force out of the integral, okay? And if I integrate from some initial position to some final position, in other words, I'm just integrating ds, right, then what's the distance traveled? It's just the displacement, okay? So in that special case, then we get the following: the work done here, the work done here is going to be equal to the force dotted into the displacement vector. And that, in this case, then, is your force times distance. Okay. But again, strictly speaking, that's only if the force is constant over the displacement. Right? If it's changing as the particle is moving, either in direction or in magnitude, then you do have to use this integral formula to get the right answer. Okay. But sometimes you'll also see it written this way, force, the magnitude of the force times the magnitude of the displacement times the cosine angle between them. Again, that's the case where you have a constant force. But perhaps the force is not the same direction as the displacement. That's possible. Okay, a little bit about work. Any questions about work? Do you remember that? If not, go back, take a look at your notes from a previous class. The other thing I want to talk about here is a little about energy. Just remind you about energy. So if we have a system with no dissipative forces, okay, anybody give me an example of a dissipative force? The chat. What's an example of a dissipative force? Okay, we got one come in, friction. Anything else? Air resistance like drag, yeah, that'll work too. Yeah, so those are some examples, friction, drag, those are common dissipative forces. If we assume we don't have those, okay, then what we know then is that the change in the potential, the change in the kinetic energy, okay, again, kinetic energy, the energy of motion, let's see, energy, I can spell that right, is going to be equal to minus the change in the potential energy. Here I'm going to use U as a symbol for potential energy. That's traditional. Okay. All right. So it says any change in the kinetic energy we get is due to a change in potential energy in the system. Right. Let me write this in a form you might be more familiar with. Here in delta means a change, right? So change. So change usually means sort of a final minus initial state. Okay. So let's see. So in other words, if we rewrite this way, and move the delta U on the other side, we'll have delta K plus delta U equals 0. Okay. If we now write out what we mean by delta K, well, that's K final minus K initial plus U final minus U initial, right? That's our change in potential energy. And if I now gather up all the final states on one side and all the initial states on the other side, we get K final plus U final equals K initial plus U initial, right? Does anybody recognize this equation? What does this tell me about energy? Yes, yes, indeed. Yep, energy is conserved, exactly. So this is our classic conservation of energy equation. Okay, conservation of energy. All right, so this and this says the same thing. It's just written a different way. Okay, so again, we're going to assume in some cases we can apply conservation of energy to help solve some problems. That's the first thing I want to remind you about. Second thing I want to remind you about is the work kinetic energy theorem. Okay, so it turns out work and kinetic energy are related. Okay, and what it basically says is that the change in kinetic energy in a system is equal to the work done on the system, right? So if I take a chair, for example, and I push on that chair over some distance, right, then I'm doing work on the chair. We know then that the chair will start to move, right? And it will then have kinetic energy. How much kinetic energy will it have? The change in its kinetic energy will be equal to the work done. That's what the work kinetic energy theorem says, okay? So forces via work to energy change in terms of kinetic energy. Okay. Any questions here? These look at least a little bit familiar. I hope so. All right. Want to also remind you a little bit about something which you may have not seen exactly this way, but you will see is familiar eventually when we get to the end of this. So we know, of course, that if we move an object with mass, back to the last slide. Okay. Okay, great, thanks. All right. We know that if we take a mass and we move it through a gravitational field, right, then it will change its potential energy. You take an object, you pick it up off the floor, it now has potential energy, okay? And the question is, can we define some sort of scalar field which can describe this change in potential energy? So for a constant gravitational field, so for example, just the force acting is mg, right? We talked about that earlier today. We can then define a gravitational field, we talked about this before in the last chapter 2, as the force on that mass divided by the value of the mass, right? We call that usually little g, right? In this case, we put a little vector over it because vector force is a vector. That's a vector field. Could we do something similarly with energy? Okay, well, yes, we can. We know how to calculate the potential energy. Hopefully you remember from Newtonian mechanics. The change in potential energy is mgy or mgh. Usually it's oftentimes you'll see it, h being the height above some reference point. That's the potential energy that you gain by taking that mass and lifting it up, right, through some change distance y. So what would be a logical way to define a potential field? Well, same way as we did for the potential for the gravitational field, take the change in potential energy and divide it, in this case, by the mass of the system. So we see then that the change in potential, gravitational potential, is now g times y. Okay. So this is something you may not have seen before, but certainly we could do, right? Energy, of course, is a scalar field, so potential is also a scalar field. It's just a number. So this turns out to be very useful for in the context of electricity. And so we'll come back to this and next time we'll define what we mean by electric potential. But it'll be done very similarly to this. Just like gravitational tells you the change in the gravitational potential energy per unit mass, we'll see that the change in electric potential chances you change in electrical potential energy per unit, in this case, charge. Okay, but we'll come back to that next time and we'll pick that up from there. Okay, so we'll stop there. Again, I will post up the slides from chapter 2. And already you'll have the review materials for the exam. We'll do the exam during the first hour on Thursday, assuming we're back to normal in class on Thursday. I will have student hours as normal today. They will be online, but I will open up a Google Meet for that, and I'll post that to I'll post it up on the announcements here a little bit in a moment. Again, student hours will be running from 1:20 to 3:25 today online. Okay, well, I'll let you go here and stay warm, and hopefully see you on Thursday.